Chapter 11, Number 8. 6 identical massless rods are supported by a fulcrum and are tilted at the same angle to the horizontal. A mass is suspended from the left end of the rod, and the rods are held motionless by a downward force on the right end. Each rod is marked at 1 meter intervals. Rank the magnitude of the vertical force F applied to the end of the rod. So our first thing is we're going to obviously want to do some torques. So I'll do this for the moment for just A. We'll say, well, we have some weight, which is 100 times G pulling down, and we have some other force. We have some force also pushing down. And what we always want to do first after identifying our forces is to identify our lines of action. So the line of action for the weight is this, and the line of action for the applied force is this, which means that the moment arm we care about will be this for the weight, and it will be this for the applied force. And the reason I want to do that is to indicate that the ratio, I don't know those lengths because I don't know the angle, but I do know that the moment arm of the applied force is still 1, 2, 3 times the moment arm of the weight. So even though there's an angle going on here, and that will change the moment arms, they'll change by the same proportion, the same sine of the angle, and therefore I can just treat them as if it was horizontal, which is kind of weird, but it doesn't really matter whether I have the picture that's drawn or if I had the horizontal version that my moment arms look like. The relative sizes will be the same. So let's compute the various torques in each case. I'm going to use, I'm going to call the force 100. I'm not going to worry about the factor of G because we know that in general the torque is the mass times G times the moment arm in this case, or it's going to be the torque of the other guy is going to be F times its moment arm. But then since I only want the scales and not the actual number, it'll be okay if I get stuff in sort of kilogram equivalents. I don't have to worry about that much. So I can look over here and say I have 100 times 1, and then I have F times 3. So that says that F is going to be something like 1/3. Should we call this? Let's leave the G in. So we'll call that 100 times G. And so I have here, it's going to be 1/3 times 100 times G. And if I do the same kind of things over here, here I have 3. And so this torque is 100 G times 3. And over here I have only 1. So this torque is just F times 1. But they're still in balance, so I know that F equals 300 G. And just doing the whole rest of the thing here, this is 2 versus 2. Since the distances are equal, I can immediately jump to say that F is just 100 times G. And then we do something similar down here, except we have 1 versus 3, but now it's 200 G versus 3F. So I have 3F equals 200 G, or F is 1/3 of 200 times G, which means exactly twice what A is. And here we have an even split, 2 by 2, which means that the force is clearly going to be 200, and then times G. And then over here we have 200 times, 3 versus F times 1. So we have 3 times 200 G equals F times 1. So F is 3 times 200 G. So not surprisingly, perhaps the doubling ends up just doubling the torques, the forces, which makes sense. So we have F is the most because it's 3 times 200, and then our next thing is going to be a 300, which is actually B, and then 200, which is E, and then C, because that's 100, which is more than 200 over 3 is sort of 60-ish. So D comes next, and then finally A.